And so here we have a pin A that is rotating about point C up here on this member AB, ABC. But then here we have this other body, colored, that is in rotation. And at the same time, this pin A is moving relative to that rotating body. So with that in mind, let's look at the textbook solution rather than me going through the whole darn thing with you on the board. So what we've done here is, or what they've done, the author has done here is, here's the slot, here's the item, the bar that has the pin rotating at 4 radians per second. And as that rotates, it's going to cause this plate to rotate. Now, they start writing their acceleration equations here, and you can refer to the handout I gave you as well as this solution that I printed out for you, and you work up the different component parts up here and then plug them in down here. And the one thing I'm not seeing on their solution is a defined axis system. So let's see if we can figure out the direction and how they set up their XY axis system.
It looks like it's below the line. It says alternatively with, I have a...
Okay, well, it looks like, I wasn't sure if they set their axis system up tilted like this. I don't think they did on that plate.
No, they put O there on the left, the origin, and then toward the bottom of the page there, they got X coming out of the end of that.
Oh, down here.
member.
Thank you.
Yeah.
Thank you. Yes. So what they did is they used an axis system. They used an axis system that's on this member. Here's our rotating member. Remember, that has the slot built in. And remember, the pin though is on this member. Right? The pin's on this member, but this is the object. This is the bar essentially that's in motion. So thanks for seeing that. So and I would have done that up here. Okay. Set my rotate, and that rotates with this member. Okay, that rotates with this member. All of these terms then are going to be written in terms of that little XY axis system. So this acceleration of A, let's see, the acceleration of point A is going to be equal to the acceleration of point P here. This is the one I was looking for right here. Here's the acceleration of point P. It's this lever arm right here times the omega of this member. And here's our omega, unknown, and it points back to that left. So this term, acceleration of P normal, P is fixed on this plate. Here's this plate here. And normal is pointing back this way. And you can see that in their polygon right here. And they show it with an arrow. And I would suggest that you get in the habit of actually, next to your results like this, is going ahead and putting a little arrow if it's convenient to lay the directions on there when you're sketching. That's going to be handy to you. Well, without going through all the detail, we've studied this kind of idea before. P is on this member. So we have motion this way, circular motion around this point O for point P, and point A is hooked on this member, so it's in rotation about this. This is the way we've studied this before, in this fashion. So this is the motion of A, and this is the motion of P, And so after a little bit of movement, then you can see that A is moving outward away from P. And what I'm looking for is the A rel term. Here it is right here. And that is in the slot, 2.72. And see how it's in the slot? It's parallel to that slot right there. So A rel has to be in that slot. Similarly, the V rel term, which is A relative to P's velocity, has to be tangent to the slot as well, up here.
So,
Yeah.
did you say that their coordinate axis that they chose is fixed with relation to the plate,
Yes,
and that it would rotate with the plate?
that's correct.
Well, then wouldn't the coincident point in the slot on the plate have zero velocity, zero acceleration, and all that?
The point P, which is locked on that plate.
Correct.
Yes, but A moves relative to P, and that's what the V rel and A rel terms are down here. And let me go back.
I'm just trying to get a graph
Yeah.
of what A sub P is really supposed to be then, if,
Yeah. Okay, A sub. It might be easier to go back and look at the velocity development before we. So let me go back to this handout, right down here. See right here, Dylan? So V rel is the velocity of A relative to P. Okay? Now, when you look at the acceleration expressions, let me go to the next page. A rel is actually a little more, the acceleration of A relative to P is a little more complex. It's made up of A rel, which is x double dot I plus y double dot j, that simple one, plus this thing, the 2 omega cross V rel.
right, which is
Yeah.
A normal.
And that's what's, this thing is there because of, we have to account for the fact that plate's rotating. And this picks it up right here. Okay. It's, I don't know if I'm going to misspeak on this or not. I believe this is going to be a Coriolis type of term. That I won't stand, I won't stand on that. Okay. So, back to the problem. When you put this all together and work up all these parts, and it's unfortunate I didn't have time today to write it out. I like to write the whole darn acceleration equation out. In other words, that, where's our starting point here? Yeah. Here's our pole right here, from which we write our acceleration equation. So the acceleration equation is that the acceleration of A is made up of the acceleration of P normal plus this 2 omega cross V rel plus the acceleration of P tangential plus A rel. And once you put that all together, you get the acceleration of A. And what falls out as you do the math, there will only be two unknowns in these equations, and you'll end up being able to find the angular acceleration of the plate and the other parts. Okay, what you can do with those other two problems, and I'm going to go ahead and just for the people potentially watching the DVD, page 183, which I showed a little earlier. Just going to put this up here for a second. Nice thing about the DVD is you can pause it and sit there and stare at it till it finally sinks in. Okay, so here's the author's solution to number 183, and here's their axis system right here that rotates on this member that has the slotted member. So this is a problem similar to what we've done before. And I showed the actual problem out of the book earlier. And they did not draw an acceleration polygon, but they did draw a velocity polygon up here. And then finally, here's the solution by the authors for the problem number 185. And we have a curved slot in this problem. And again, they were pretty good about writing the axes that we're rotating now with this slotted member. Once again, they did draw the velocity polygon because those are usually relatively simple, but they did not draw the entire acceleration polygon. Okay. If this class was longer in duration, we would definitely cover this material and give you the chance to work problems out using this as a technique. Okay. There was, now as far as wrap-up goes for the course, there was something that I think I'd handed out to you back from chapter 2, and I believe it's a mistake that the authors had made in one of their solutions. This was back earlier in October, or in May. Yes. And actually, I want to go back to that for a couple minutes to sort of point out how easy it is to make a fundamental type of error. This is back on page 65 in the textbook. And this will be a good kind of a review idea for you, or concept for you. I gave you a handout, but I don't believe I spent class time on it with you.
123.
Yeah, this is number 123 on page 65. This is tape drive problem. Yeah. So here's a subtlety that I want to point out to you, and then I'll show you for the people that might watch the DVD someday. I'll put the hand solution that we worked up here on the overhead. And while I'm at it, I will see. Do I have the author's work there? Yeah, here it is. Let's see if I can show you their solution at the same time as we have the picture there. Let's see if I can get this to, yeah, here we go. This will be adequate. There, good. Okay, so here's the author's solution at the bottom. Up in the wording of the question, we have flat tape, a numerical control device. It's changed by two pulleys, A and B, as shown. The speed of the tape increases uniformly from 2 meters a second to 18 meters per second, while 8 meters of tape pass over the pulleys. So what's going on, at least the way I'm reading this, is that as 8 meters of tape passes over the pulleys, the velocity grows from 2 to 18 meters a second. Right? Okay. And then they said calculate the magnitude of the total acceleration of point P, which is up here on this 150 millimeter wheel, at the instant when the tape speed happens to be 3 meters a second. And look at their solution. They came down here and they grabbed this equation, which is based upon a constant tangential acceleration. Well, if you think about that graph, of velocity, you think of it as changing nice and linearly, right? But it's not changing linearly over time. It's changing linearly over distance, over displacement. And I'll show you what I did on the handout. So they made that assumption. They used this equation, which they even cautioned you about this, and I cautioned you early in the course about don't use this equation. Always operate these things from the differential equation, from the original differential equation. And so they just went ahead and dropped this in, 18 squared equals 2 squared plus 2 times AT, 8, to get the acceleration that they said is the tangential component. And then they figured out, once they knew that tangential acceleration, and they wanted a speed of 3 meters per second going on when the tape reached that value. So the normal acceleration would be this, and then they just dropped looked at the Pythagorean relationship there to come up with that answer. Okay. So let me refer you back a few pages in the book. To something that I did not cover with you, or did not speak of. It's in the book. It's actually back here on page 24. Now take a look at this. There's a nice concept here on the bottom of page 24. If we have velocity described as a function of position, then it should make sense to you that the tangency on that graph, and this is actually the way oftentimes you gather experimental data. You can monitor the speed of an object and its position, and then you could plot that data. And then separately, you might be picking up the time, the behavior with time. But if you gather this kind of data and plot this up, velocity versus position, then the slope on this graph is going to be an infinitesimal, the rate of change of dv, or v, with respect to s. That's going to be dv ds for a rise for a run of 1, right? So that's the slope of the tangency. Now, if you then draw a perpendicular to the tangency and use equal scaling, in other words, a meter per second here is going to correspond to a meter of spacing down here. So if you use equal scaling on it and you draw a perpendicular to the tangency here, then this height right here is v. Well, look at this relationship then. dv ds, the slope of this tangency, has to be then equal to this distance bc divided by v. But look at that relationship. That means v dv equals bc ds. Well, that's our differential equation, where the measurement of bc is a measurement of the acceleration at that location, at that speed. Okay. Now, the handout that I had given you, and there's some discussion here in the text. I'll just move that over here for just a second, if somebody wanted to read that. Okay.